Okay, so hi everyone. Thank you all for being here. Today I'm thrilled to introduce you to Hayden Lee from the University of Chicago. A little background about Hayden. He obtained his undergraduate studies at the University of Canterbury in New Zealand. Then he obtained his master's and PhD at Cambridge University. He also held a postdoc position at Harvard University, and now he is a postdoc at University of Chicago. Some of his research interests includes physics of the early universe, bootstrap formalism for inflationary cosmology, and statistics of large-scale structure of the universe. Today, he's presenting about inflationary correlators from the boundary. So thank you, Hayden, for accepting our invitation, and you can start your talk when you're ready.
All right, so thank you very much for the nice introduction and the invitation. It's a great pleasure to be able to virtually visit Universidad de Chile and give this talk. So today I'd like to tell you a bit about the work that I've been pursuing on the subject of inflationary correlation functions with this particular set of collaborators over the past few years. So basically what we've been trying to do is to develop some new way of understanding these inflationary correlations from a particular point of view, a point of view in which we try to get rid of the ordinary space-time picture and focus on observables on a purely spatial boundary, which is what this title is about. So I'll try to explain what I mean by this and share with you some of the exciting new developments that we've made throughout this pursuit. And also, yeah, people are free to interrupt if they have any questions during the talk. Okay, so let me get started. All right, so I know that there are a number of experts in cosmology in the audience, but let me just use the first few minutes just to briefly describe the big picture so that everyone's on the same page and try to motivate why we are doing this. So in cosmology, our main goal is to use late time observations of the universe to really learn something about fundamental physics and the origin of structures in the universe. Okay, so in this pursuit of understanding the universe, the first thing we could ask is what are the observables in our universe that are useful for doing this fundamental physics? So for example, we are not really interested in, say, the positions of individual galaxies in the sky, but what we are really interested in whether there exists any non-trivial correlations between the positions of galaxies. So suppose we observe a galaxy at a particular position on the sky, and the kind of question we could ask is whether there exists any, what is the probability of finding a particular galaxy as a function of the distance away from this galaxy, okay? And this is the information captured by the two-point correlation of galaxies, okay? So we can ask what information specifically do these two-point functions carry. So if these galaxies happen to have undergone completely different lifetimes and evolutions of their own, then we would just find that their correlation is just given by some random noise, in which case we wouldn't be able to extract any physics, interesting physics out of it. And that could be a sad ending for early universe cosmology. But fortunately, that's not the case. And instead, the measured correlation functions show a very specific shape, which in Fourier space looks like this particular form, which we all know and love, the matter path spectrum in Fourier space. And from this shape, we understand that these galaxies really originated from some common source in the past, starting from some initial condition at some very early time. And also the measurement of the CMB power spectrum suggests exactly the same thing, that these late time fluctuations really had originated from some common seed fluctuations in the past. Okay. So what we'd like to do is to measure these correlation functions of various cosmological structures at late time. And by running the clock backwards and tracing these correlations back in time, we want to try to reconstruct a consistent history of the universe in the past that explains the origin of these correlations. So the initial condition for these perturbations in the universe, we think of is as given by some correlations of the primordial curvature perturbations, labeled by zeta, defined on some reheating surface near the beginning of the hot Big Bang. Okay, so we don't know exactly when this happened, but we think that there's an initial condition imprinted on this specifically this reheating surface near the beginning of the hot Big Bang. And the key fact we have discovered from these measurements is that these late time correlations seems to have been generated from a remarkably simple initial condition described by a nearly scale invariant power spectrum of this curvature perturbation. So the question we are naturally led to is what cosmic history gave rise to these primordial fluctuations in the first place with this seemingly special initial condition. So as you know, the standard picture is that these primordial fluctuations are thought of as being generated during cosmic inflation, which by definition is a period during which the universe undergoes an accelerated expansion. So this inflationary background is described by an approximate four-dimensional de Sitter spacetime, whose metric takes this particular form. Okay, so this is the FRW metric in conformal coordinates. So here H is the Hubble scale that sets the rate of the expansion during inflation, and eta here is conformal time. So in this picture, what's going on is that because the universe expands exponentially, these tiny quantum fluctuations that are produced at some earlier time during inflation get stretched out to macroscopic distances during inflation. They exit the horizon and freeze out, and then become seeds for all the late time structure formations. Okay? And due to the isometry of this particular de Sitter metric, inflation naturally predicts a near scale invariance of the fluctuations, which is precisely the special property of the two-point function that we have observed from data. Okay, so from observations of the two-point function, it seems very likely that there was some sort of an inflationary expansion in the very early universe during which these primordial fluctuations were quantum mechanically generated. But a number of questions still remain about the very nature of inflation. For example, we don't have too much clue about the precise microscopic mechanism that gave rise to these primordial fluctuations. Neither do we know about what kind of particles existed during inflation. So in order to gain a more complete understanding of the early universe, it's going to be extremely useful to measure these correlation functions beyond just the two-point function. Okay. So although the measurement of the two-point function was very nice in that it basically established the inflationary paradigm in the first place, the information carried in it is quite limited because it's essentially parameterized by two parameters, the amplitude of the fluctuations and a small deviation from exact scale invariance. But instead, most of the dynamical information about inflation will be encoded in these higher point functions. So this picture, for example, shows some possible types of correlation functions we could imagine having during inflation. So in this picture, conformal time runs upwards. And what's going on in this picture is that particles interact in the past, sometime during inflation, and then they eventually evolve and exit the horizon and form these late time correlation functions at very late times, essentially at this eta = 0 future boundary of this little space-time. Okay. So for example, a three-point correlation could arise from some sort of a self-interaction of particles in the past. We typically think of this as the inflaton fluctuations. Okay. And then we could also imagine having some heavy particle during inflation that decays into these pairs of inflatons to form this four-point correlation on the boundary. And unlike the two-point function, which is just a function of the distance between the 2 points, oops, sorry about that. Okay, so unlike the two-point function, these higher point functions really depend on the entire three-dimensional shapes formed by these various points. So they can just constraining a single shape of this higher point function can tell us very specific information about various particles and the interactions that generated them. Okay, so given the importance of these objects in understanding the nature of inflation, as theorists, we'd also like to have a framework for systematically computing these correlation functions and make predictions for possible shapes that people can actually look for in observations. So as a very simple setup, let's look at this diagram again. So we can imagine that there is some heavy particle that decays into the inflatons to form this four-point correlation. And because we are really computing correlation functions of quantum fields, the standard framework for computing this correlation function is QFT in digital space-time. So in this framework, you can basically write down some Lagrangian for the theory and then start computing Feynman diagram for this scattering process. Well, this is possibly the simplest scattering processes you could imagine having between two particles, right? Just a tree-level process. And if you were to do the same calculation for the, say, for the scattering amplitude that corresponds to this process. So for example, imagine computing this tree-level scattering amplitude in flat space. Then essentially we don't have to do any calculation. The answer for this object is given by just p squared over m squared, the usual propagator in flat space. But it turns out that in the context of inflation, computing this type of correlation functions turns out to be extremely complicated. So it actually may surprise some of you that this particular tree-level 4-point function wasn't really computed until just a few years ago. Yeah, despite the subject of Lagrangian having been around for 20 years.
Sorry, Hayden, I have a naive question. Why do you commit so early to have a heavy particle? Could this be a light particle, for example, or is there any reason to?
Yeah, so yeah, this can be any particle, so it doesn't have to be a heavy particle. It can be some massless particle or a very light particle. For example, you can even imagine having this to be the inflaton itself. So inflaton can self-interact with the cubic interaction and then generate this 4-point function. Yeah, so these heavy particles have gained attention recently because they happen to give rise to very specific signals which are distinct from the exchanging very light particles. For example, you will see that, yeah, in the end, I'll try to mention some shapes of these correlation functions. So if you were to plot this, as you very well, if you plot this, the shape of this 4-point function as a function of some momentum, if you have a light particle, it will have a very smooth shape as a function of k. Whereas if you have a very heavy particle, it will produce some oscillations, which are very distinct from these light particles. Yeah, so in fact, if you're exchanging a massless particle, this type of correlation function has been calculated many times, and they're relatively easy to compute. But for heavy particles, for the reasons that I'm going to explain, it's very difficult to compute. Yeah, essentially the reason is that, yeah, computing this correlation function boils down to computing integral of this form. So the reason for complication is that in cosmology, we don't really have time translation. So we have to do these explicit time integrals in conformal of time. It basically evolve these particles in an inflationary background. And the complication is that this heavy particle propagator is given by some time-ordered part of the Penka function, as you know very well. And because of this time ordering inside the integral is very complicated, and it wasn't known how to evaluate this type of integrals analytically. Okay, so at least this brute force way of computing these correlation functions for general processes involving heavy particles seems quite complicated. And also, we may also think about computing correlation functions of spinning particles, such as those of massless spin 2 gravitons that give rise to primordial gravitational waves. They have also a lot of attention recently. And it turns out that we know very little, relatively little about these correlation functions of spinning fields, which is again primarily limited by the difficulty of computing these diagrams using the traditional method. So to make progress, we think that it will be very useful to develop some new theoretical approaches to attack the problem. So with this motivation, the so-called Bootstrap approach has been developed recently, which has provided some new insights into the problem. So what exactly is this Bootstrap and why it's useful? Well, ultimately, the reason why we are doing these theoretical calculations at all is to make some predictions so that observationalists can look for them in actual data, right? So we want to know what is the most efficient way of getting to this final observables that we want to directly compare against observations. Well, in order to compute this observable using the textbook field theory approach, we usually write down a Lagrangian for the theory involving some fields and go through the usual steps of computing Feynman diagrams. The downside of this approach, while being very systematic, the downside of this approach is that Lagrangians and fields are something that are not truly fundamental, but in fact they are quite something quite the opposite, being intrinsically redundant, because final observables should be invariant on the arbitrary field redefinitions. Okay. So in principle, there are infinitely many Lagrangians and field descriptions that produce exactly the same final on-shell observable. On the contrary, the defining philosophy of the Bootstrap approach is that it wants to bypass all these usual steps of the computation, and instead its philosophy is to focus directly on the final on-shell observables. And the idea is to basically start from some basic cherished physical principles like symmetries, unitarity, and locality, and then try to find objects that are fully compatible with those principles, with the hope that these are enough to fully determine the observables from a given set of assumptions, or at least put very strong constraints on the allowed types of observables we can get. Okay. And I'm sure many of you have already know, or at least heard of, this Bootstrap perspective has been particularly influential in other areas of higher energy physics, such as the studies of scattering amplitudes and conformal field theories. So we are basically motivated to see whether a similar strategy can be also useful for our cosmological problem. Okay, so coming back to cosmology, the goal of what we may define as the cosmological bootstrap program is to try to use a similar consistency requirement to directly find the answers for these final cosmological correlation functions without necessarily following the usual bulk space-time dynamics or directly computing Feynman diagrams. So again, this perspective has the conceptual advantage that it directly focuses on the observable, final observables, which are these boundary correlation functions. Okay. So we can directly ask what physical constraints that these final observables need to satisfy without having to deal with some redundant description in the intermediate process. And of course, more practically, the calculation of the correlators will also become a lot simpler in this new approach, as I'll mention later in the talk. So this enables us to compute many new interesting classes of correlation functions, as well as easily reproducing the previously known results as well. So, so these are basically the motivations, and now I'm going to give you some pedagogical walkthrough of some of the main ingredients of this approach. Okay, so here's the outline for the rest of the talk. So the plan is basically to first describe what these physical principles are and look at the consequence of each of these principles on correlations. Okay, so first I'm going to talk about the various types of singularities of cosmological correlators. So we know that mainly through complex analysis, the knowledge of singularities of a function largely dictates its analytic behavior. And we'll see that these singularities contain the information about the flat space limit. And thus I will provide the relationship between these cosmological correlations and the scattering amplitude in flat space. So I'll talk about that in the beginning, and the next I'll describe the consequence of unitarity on these correlation functions, which we'll see that it implies a specific cutting rule in cosmology. And then I'll describe the symmetry constraints on correlation functions, especially the ones due to the so-called SCT constraints or special conformal transformations. Yeah, I probably won't have time to get to the last part, but if I do, I'll also mention how correlation functions of spinning particles can be obtained by introducing a certain set of differential operators. Okay, so perhaps I should stop here if people have any questions about the introductory part.
I have a question. I mean, I like very much your introduction, but would you dare to mention some something against this approach? Like, okay, there are some situations where perhaps the Lagrangian approach is preferable, or do you commit fully with this approach? What's your opinion on that?
Right. Yeah. So certainly there are some problems where the Lagrangian approach is useful. For example, yeah, the much of this analysis will strongly rely on the symmetries of the background. So for example, conformal symmetries, this SCT constraint will put very strong constraints on the types of correlation function we can have, but you can imagine having some more general inflation scenarios where these symmetries are completely broken. So in those situations, it's not clear which principle to use to constrain these correlation functions. And yeah, it may be more useful to actually start from the Lagrangian approach to do some explicit Feynman diagram computations. So this kind of approach has not replaced like all the previous calculations that applies to more general inflation scenarios. For the purpose of the talk, I'm going to consider like very specific minimal inflation scenario where things are, space symmetries are minimally broken. So we consider a very slow rolling background with weak interactions so that we are very much around the pure de Sitter spacetime.
But if you, for example, break some of the symmetries, will there still be general rules that applies, for example, from the analysis of singularities or unitarity that have to stay in the game? Will that be correct?
Right. Yeah. So very good question. So in fact, while the symmetries can be broken in general inflation setup, types of singularities and the unitary constraints will actually also apply in those more general inflation scenarios. In fact, this will even hold in general FRW spacetime, not just in inflation. Basically, the information about singularity is the locality information. So the fact that the correlations was generated by some local interactions in the very past. So singularity basically captures the locality information in the past. And unitarity, of course, should be obeyed in any space-time background. It's just a statement that the probability of scattering is equal to 1.
Okay, thanks.
But these so these two types of constraints will apply to any cosmological background, but then these are also not enough to fully fix the form of the correlation function. So we have to combine with some stronger principles like symmetries in order to fully fix the correlation functions.
Just a question related. I wanted to ask later, but since we brought it up here, so you could also think, I don't know if you have thought about it, but symmetries during inflation are softly broken. For example, you deviate slightly from de Sitter, incorporating slow roll. Is there any continuous deformation of the symmetry group of de Sitter? I like thinking out loud, right? That like quantum groups and stuff like that, where and maybe you can use representation theory of these extended algebras, let's say, and play the same game. Have you ever thought about this direction?
Yeah, it's also a very good question. So essentially, what we'll be doing is to do the calculation in exact de Sitter spacetime, but the question is how to extend this to slow roll inflation scenarios. Essentially, there's going to be some sort of a slow roll expansion. Expansion in the slow roll parameters that allows us to go beyond the time. So for example, we'll be interested in computing correlation functions of massless scalar field, but we know that the inflaton is not exactly massless because it has to roll down the potential. So we will have to give a small mass to the this correlation function and then expand in the small mass of the inflaton parameters, and that will allow us to compute the inflation correlation function. Yeah, that's a very good point. Okay, so let me move on to talking about the singularities. Okay, so actually before going to details, I'll first admit that I'll be actually using a slight abuse of terminology so far, which is that the object I will be mainly talking about is not going to be correlation functions themselves, but in fact it's something called the wave function of the universe, denoted by this sign, although these are very closely related. So just to explain the motivation for going to this, showing a picture. So just as in ordinary quantum mechanics, this wave function captures the probability of starting from some vacuum initial state in the past, which we typically pick to be the Bunch-Davies initial state. And then the the probability of this state evolving into some particular field eigenstate at a later time. And one can compute correlation function from the knowledge of this wave function, which can be done by doing this usual path integral, where the probability density is given by the square of the wave function. And in perturbation theory, where these fluctuations are small, we can expand this wave function around the Gaussian piece, plus some high order terms in this way. And what's going to capture the information about individual correlation functions of phi are going to be this what's called the wave function coefficients, labeled by this little size in red. So for example, doing the usual Gaussian path integral, the 2-point function will be just given by the inverse of the real part of this psi 2. And similarly, the 3-point function of phi is going to be some combination of psi 3 and psi 3 star. In this way, normalized by some psi 2 structures. And it turns out that it's useful to think in terms of these wave function coefficients because they happen to satisfy some nicer properties compared to correlation functions. And intuitively, this is because the wave function is an object which is really analogous to the S matrix in flat space. So just like the wave function, the S matrix captures the probability of starting from some in state to out state. And but this is not an actual observable because we have to square the S matrix and the integral of the phase space to get the actual observable, which is the cross section. So just like that, the wave function coefficients are in some sense more primitive objects compared to correlation functions because they are computed from this wave function coefficients. But having this in mind, from now I'm also going to be somewhat loose about the terminology again, and sometimes just refer to wave function coefficients as correlation functions. But strictly speaking, the properties that I'm going to mention apply to the wave function coefficients. Okay. Right. So just to begin, let's take a look at some simple examples, just to get some flavor of what the structure of this wave function coefficient look like. Okay. So we can try to look at this 4-point wave function coefficients from some simple tree-level processes. And to make the problem even simpler, we're going to imagine that these are wave functions of massive scalar field in flat space. Okay. So in this case, this t will be just a ordinary physical time. So basically, this will be the same calculation that we'll be doing in cosmology, except that we are setting the scale factor exactly equal to 1. Okay. But it's useful to take a look at this for example, because many of the features will continue to hold once we have generalized to this space and inflation. Okay. So the wave function coefficient can be computed in this standard Feynman diagram computation with some boundary conditions. So the only difference will be that the only difference from the standard S matrix calculation will be that we will be integrated only up to this feature boundary defined at t equals 0. Okay. So if you look at this contact diagram and then integrate up to this boundary of this both the boundary propagators, which is given by this standard plane waves, what we'll get is this simple answer that looks like 1 over E, where E is the total energy of the process defined in this way. Okay. And also another process we can consider is the simple tree exchange diagram. So in this case, we'll have to evaluate 2 time integrals connected by this propagator. Okay. I won't write down the express form of the propagator, but this integral can be done in a simple way and give this final answer, which is given by this 1 over 3 factors of energy variables, where E left and E right are defined as the total energy flowing into the left and right vertex. Okay. So these energy variables are defined in this following way. So from looking at this in the examples, we notice a particular feature that this wave function coefficients happen to become singular when these energy variables goes to 0. Okay. So so what is the origin and interpretation of the singularities? Well, as I mentioned earlier, these are really the avatar of locality of the interactions in the past. But we can also think of this as the really being the analogs of the energy conservation conditions for scattering amplitude in flat space. So to see why in the standard amplitude calculation, suppose you want to compute this amplitude for this 4-point contact interaction. In this case, we'll be integrating not from minus infinity to 0, but to plus infinity, okay, of this plane waves. And this will give rise to a delta function that basically imposes energy conservation. So the only difference here in cosmology is that we are integrating only up to t equals 0. So instead of the delta function, we have this pole in the energy variable. Okay. And the interpretation of this pole is that suppose we're going to the singular limit where we set e to 0. Okay. In this particular limit, basically we are setting this oscillatory plane waves to 1, right? So in this case, this integral actually blows up because it has infinite contributions that are coming from minus infinity. But in that particular limit, because the integral is dominated by this contribution from minus infinity, it will lose the information about the boundary that exists in the future. So we are expected to reproduce the answer in flat space limits. Okay. So the upshot is that the coefficient or the residue of this total energy singularity at E equals 0 precisely is given by the corresponding amplitude in flat space. Okay. And this happens to be even true for wave functions in arbitrary FRW or de Sitter spacetime. And essentially the argument is that at very early times, all the modes are well within the horizon. So they don't really feel the curvature of spacetime in the future. And in the very early time limit, this propagator simply becomes reduced plane waves. Okay, and you will see that when you set the energy, total energy of the process to 0, the integrals will blow up in the same way as before. Okay. The only difference is that there can be some extra factors of eta in the time integral, so we can get some higher order poles in this total energy, not just a simple pole. Okay. So it turns out that this is a very non-trivial condition that all cosmological correlations need to satisfy. And also there's a similar type of singularity for the exchange type of diagrams. Okay, so namely when the energy at each interaction vertex goes to 0, rather than the total energy. So in this limit, what we are essentially doing is that we are dragging each of these interaction vertex all the way to past infinity. So in this limit, what we are doing is that we are cutting the diagram into 2 halves, where on the left vertex we are reaching this flat space limit for the left interaction, and on the right will be some 3-point wave function structure remaining. Okay. So here, to be more precise, the 3-point function appears on the right-hand side is something called a shifted wave function with this tilde notation. Okay. So this is defined as just the difference between the ordinary wave function and the one with the flip sign of the energy. Okay. So I'm going to explain where this precise combination of structures comes about in a bit. Of course, we can do the same for the right energy and vice versa. So it turns out that these poles in the energy variables are the only possible types of singularities of correlators of massless particles at tree level. Okay, so the idea now is to use this information about singularities to see if we can bootstrap the full wave function away from these singular limits, and find an object that reduces to this correct flat space limit in all singular limits. Okay, it turns out that it's yes.
No, just a question. In these schematic expressions that you have, are all diagrams in the flat limit, or some of them are, others are not? Like the how do I understand, for example, that product?
Oh, so yeah. So essentially, so suppose you have the full expression for this 4-point function. So it will be given by some e to some power, e left to some power, different power, and e right to some power. And in the numerator, it will be some polynomial in the momenta. Okay. So this is the general expression that you want to reconstruct eventually. But if you take individual limits, then, for example, if you take e to 0, this particular combination, the remaining combination will combine in such a way that it will produce the Lorentz invariant answer that becomes this classified amplitude. So you can take the full correlator, so full wave function, and then consider this individual limits. But now the exercise is that we don't know this full answer, what this full answer looks like, and we just know what this singular limit becomes in these individual limits. And then using this information, we want to reconstruct the final correlation function.
I see. Thanks.
Hayden.
Yes.
Is there any particular reason well, any physical interpretation of the n of the order of the pole or m?
Yeah. So good question. So as I said, this is fixed by some extra factors of eta that appears in the time interval, and the origin of the extra factors of eta is the so number of derivatives of the interaction. So the higher number of derivatives, the more it will be suppressed
Okay.
in this so that you have higher powers of this pole.
Okay. Thank you.
Yeah. All right. So yeah, in the toy examples that we looked at before, the wave function in flat space, they just have simple poles. So it's very simple to reconstruct the full wave function. But in de Sitter space, it's not enough to know the singular behavior, but you also have to know all these subleading corrections, which is a little bit more complicated. So yeah, recently a relation between the full wave function and its factorization is found beyond this singular limits. So this condition is basically derived from the unitary condition and has been dubbed the cosmological optical theorem or a cosmological cutting rule. So this is a direct consequence of unitarity, which relates some sort of a discontinuity operation of a correlator to its factorization. So in this diagrammatic representation of the formula, on the left-hand side, we are taking a sum of the ordinary wave function and its complex conjugate with some flipped sign of the energies. And what this mathematical operation does precisely is that it basically cuts the diagram into two halves, where each half is given by these shifted wave functions. Okay. So this is a precise analog of the familiar optical theorem for amplitudes, which has this well-known form. So yeah, as I was mentioning, this formula is going to be practically useful as it completely generalizes the factorization behavior even away from this previous singular limits, okay, and can therefore fix this subleading singularities, this expansion. So notice that we haven't taken any singular limit in this equation. So what I want to do next is to explain how this cutting formula actually arises for cosmological wave function as a consequence of unitarity. Okay. Yeah. So before getting to the cosmological cutting rule, let me take a step back and consider the analogous problem in flat space, which should be more familiar to many of you. So this is going to be useful because it turns out that the derivation of the cutting rule for cosmology is essentially goes in the same way as I mentioned in a moment. So basically, the cutting rule follows from a certain property that the Feynman propagator satisfies in flat space. So for this purpose, we can consider two types of Feynman propagators. One is the ordinary Feynman propagator with the I epsilon prescription. And the other is the anti-Feynman propagator, which is just given by the complex conjugate of the ordinary Feynman propagator with the opposite sign of the I epsilon. Now, the cutting rule basically boils down to simple identity that this propagator satisfies. So namely, if you take the difference between these two propagators, or just to take the imaginary part of this ordinary Feynman propagator, we will get a delta function that puts the propagating particle on shell. Okay? And the usefulness of combining the propagator in this particular way is that we can get rid of the time ordering of this process of the propagator. So basically, on the right-hand side, we don't have any time ordering because there's no epsilon in this expression. Okay, so basically that means that if we insert this particular combination of propagators in the amplitude, it will factorize the amplitude into lower point functions joined by some on-shell particle. Okay. All right, so what we want to do next is to define two types of scattering amplitude for formed entirely entirely in terms of the ordinary Feynman propagator versus the anti-Feynman propagators. Okay. Now we want to take difference between these two amplitudes, and by repeatedly using this particular identity between the two propagators, you can show that this difference is given by the sub amplitude, the combination of lower point amplitudes, where at least one of the internal line is cut. Okay. So notice that so far we haven't used anything about unitarity because this is just an identity, a combinatory identity that is supposed to hold even for non-unitary theories. And the reason this identity is not yet useful is because this anti-Feynman anti-amplitude is not a physical amplitude. It's just some amplitude, some unphysical amplitude formed entirely in terms of these anti-Feynman propagators. But this can be related to physical amplitude in unitary theories because this A bar is just given by the complex conjugate of the ordinary amplitude. So the final form of this cutting rule is given by this this expression where we take the imaginary part of the amplitude. It will induce all the cuts at least for at least one of the internal lines. Okay. So this is the standard optical theorem for flat space, and yeah, as we'll see, the derivation of the cutting rule in cosmology follows in exactly the same manner. So as before, we can consider two types of propagators for the wave function, okay, which is defined to be G and G bar. So here I'm showing you the explicit form of the propagators for this the so-called conformally coupled scalars, but essentially the same derivation goes through for any generic massive particle. So here, in contrast to the flat space propagators, we have this explicit data function appearing because we have not Fourier transformed the time variable. If had we done that, this will be just corresponding to ordinary Feynman propagator, but there's an extra boundary term we have to add in this propagator just to impose some certain boundary condition at late time surface. So actually, the detailed form of this propagator is not going to be very important, but the important point is that if we combine these two propagators in this particular way, again, we'll get rid of the time ordering in the process. It will basically effectively cut this diagram into two halves. Okay? And we see that this particular combination of the propagators appear. Essentially, this gives rise to this tilted wave function. Because as we saw before, it's a difference between the two wave function with the flip sign of the energy, and essentially this is what happens in this when we cut this propagator in this way.
Hayden, I have a question. Could you go back? Yes. So I'm a bit confused. So this boundary term in the propagator, you said that you had to add it manually, or it's sort of like appears naturally when deriving the propagator?
Oh, so yeah. So basically, the propagator satisfies this equation. Okay, ordinary Green's function equation. Then we want to solve this Green's function equation with a particular boundary condition so that when we compute this kind of wave function, this Green's function actually vanishes towards the boundary. Okay, so this is some extra boundary condition we are imposing, and that gave rise to this extra term in the propagator.
Oh, okay.
When you just solve the equation.
Okay.
And sorry, why do you impose that condition? I mean, that's not the same as requiring that the 4-point function vanishes, or is it something else? Am I?
Oh yeah, so this is something else. So actually, yeah. So in computing this wave function, so this wave function actually defined as some sort of a path integral of the e to the is. Okay, so when you compute this actual wave function, the way we do it is actually to compute some. Sorry. The way it's formally defined is that it's defined as some path integral of the action, which is the usual definition of the wave function. So we have to impose a certain boundary condition for this phi field. And the boundary condition that we are imposing is that at earlier time, this satisfies the Bunch-Davis initial condition. Okay, so this is ED vacuum. And at late time, we are imposing the condition that the particle, these fields become completely classical. So that we can essentially compute this wave function using some on-shell action in the semi-classical way. So that particular boundary condition that we are imposing at future boundary is the condition, is the extra term that we are getting in this range function.
I see. Thank you.
So, yeah, that's right. Yeah, it's somewhat similar to the extra terms that we get from the usual inning calculation, which is different from the usual flashback calculation, which just involves the Feynman propagator, whereas in an inning computation, we have to add some extra terms into those. Well, that basically tells us that we are computing the in correlator compared to in-out correlator. All right. Yeah, so basically we can go through the same process of defining these two types of wave functions, the ordinary wave function and the anti-wave function. But just by some combinatorial identity involving this particular formula, we can show that if you add these two wave functions together, it will involve the lower point wave functions involving at least one of the internal lines cut. However, again, this is not, as it stands, useful because this anti-Feynman propagator is not a physical, is not related to the physical wave function. But it turns out that we can do this for unitary theories again, where this psi bar is related to taking the complex conjugate of physical wave function with the flip sign of the energies. Okay? The reason why we have to flip the sign of the energies is that because these external propagators, if you remember, at this e to the IKT, sorry, e to the IK eta. So taking the complex conjugate of the ordinary wave function will flip the sign of the external wave numbers, which is why we also have to flip these external wave numbers on top of the complex conjugation. So the upshot is that we get this final form of the cutting rule, which involves taking some discontinuity of the wave function on the left-hand side, and it will effectively cut the diagrams into many different pieces. Okay.
Sorry to interrupt you again. You haven't imposed symmetry yet, or at least you haven't.
I haven't imposed any symmetries yet. Yeah, so there will be actually the next out of the talk.
But nevertheless, in your previous slide, you have explicit expressions for the wave functions, for the model functions, let's say, and these look like.
That's right. Yeah.
Yeah.
Mm-hmm.
So isn't that already adopting some sort of behavior of the background or something related to symmetries after all, or this is just for making statements and this will be true for any background in the end?
That's a very good question. Actually, yeah. So here I'm showing you the explicit expressions in this background for this complement coupled field, but it actually turns out that this particular identity holds even for FRW spacetimes. So if you were to compute some propagators for generic particles in an FRW spacetime, they will essentially obey the same identity due to this specific boundary condition that we are imposing for the wave function.
Okay, so the boundary condition, it's important, but it doesn't rely on the actual background.
That's right. Yeah.
Okay. Thanks.
Yeah. Thanks for the question. Yeah. Okay. Yeah. So the cutting rule is very nice because it doesn't rely on the specific background we are in. So these formulas are also useful for doing the actual inflationary calculation in generic models. Okay, so these are some examples that this cutting formula is useful for. Okay, yeah. So next I'll talk about symmetry. So yeah, so far I talked about this energy singularities appearing as poles in the energies, but that's usually true for correlation functions involving massless fields or conformally coupled fields. for which these propagators are very simple rational functions. However, if you're interested in computing some correlation function for generic processes involving some heavy particles, say, we're going to need something even stronger to fully fix the form of the wave function. So next I'll go to talk about the constraint due to these extra symmetries that we have in this data background. So as you very well, in FRW, we have this usual spatial rotations and translations that puts this 4-point function in this particular form, where we have this delta function imposes spatial translation symmetry. And this function, which I'm calling f, has to be some dot products involving this external momenta to obey spatial rotational symmetries. But in this little space-time, the extra symmetries that we have from the background actually act as approximate conformal symmetry on these late-time correlation functions. So these are the extra symmetries that we have. One is the dilatation, and we also have 3 SCT symmetries, spatial conformal transformations. Okay, so yeah, so let's try to look at the consequence of the symmetries, specifically for this conformally coupled scalars, for which the action of the symmetries is the simplest. But as I'm going to briefly mention later, there's a way of starting from these simpler objects in terms of wave functions of conformally coupled scalars to generate some more generic wave functions involving massless particles or spinning particles and so on. Okay, so we want to first compute, be able to compute this 4-point function involving conformally coupled scalars. And the constraint due to dilatation and spatial conformal translations actually turn into this particular differential equations that this 4-point function needs to satisfy. The first of which is given by the dilatation constraint, and we see that this basically imposes the constraint that f needs to have scaling dimension of -1. Okay, so we can basically solve this constraint by pulling out some momentum variable, and it's useful to do it by pulling out this internal momentum defined to be ki in this way. Okay, and the rest we want to solve for the conformal special conformal constraint for this dimensionless function f hat. Okay, here I'm just to define this dimensional variable to be a function of this dimensionless ratios of momenta in this way. But the nice thing about this definition is that this previous spatial conformal transformation constraints, which is ugly partial differential equations, turn into this nice differential equation, second order differential equation, involving some hypergeometric second order differential operators, which we can actually try to solve. Okay, so the idea is that, okay, so here we've just imposed the kinematic constraint of conformal symmetry. And the idea is that we want to solve this equation for some simple dynamical processes, starting at tree level first. Okay, so we can try to solve this equation for some contact interactions and then exchange processes. And once we have solved this object in pure de Sitter space, we want to also generate some inflationary functions, as Cypress was mentioning earlier in the talk. And that can be done by expanding this external mass of the particle in the Sorel parameters. Okay, so yeah, let me just briefly mention how this equation actually can be solved for these processes. So yeah, first we can look at the contact diagrams. So these contact diagrams can be classified by just starting from this 1/E, which was the simplest solution for the contact wave function we saw before. Okay, turns out that the simplest solution is basically exactly annihilated by this this operator. Okay, so this 1/E is actually conformally invariant. And then starting from this object, we can construct all the higher contact solutions by simply acting with this higher powers of this delta U operator. Okay, and this higher powers will correspond to contact interaction generated by this higher derivatives in the Lagrangian. Okay. All right. So having obtained this contact solutions, we can also try to solve the exchange equation. So yeah, I'm going to skip all the derivation, but essentially the exchange for 4-point wave function satisfies this particular ordinary differential equations in U and V separately. Okay, and there's a simple way to understand this equation, which is by taking the large mass limit of this equation. So mu is essentially the mass ratio in Hubble units. And when the mass becomes very large, we can effectively integrate out this particle. So in this limit, this 4-point function will just become proportional to the contact diagram because we have integrated out the particle. And that's what you basically see in this equation. And it's kind of amusing to see that we essentially have very similar expression for flat space amplitude, which is just given by this this form. So you can essentially think of this delta U operator as being some sort of Mandelstam variable. Okay. So yeah, it turns out that you can actually go about solving this equation, which gives rise to some complicated hypergeometric function. But actually, the solution becomes very simplified if you take the so-called squeeze limit of the correlator. Okay. So here, after solving for the 4-point function, you want to take the soft limit of the 3-point function. So basically, take the momentum of one of the legs to be much smaller than the other leg. And when you do that, the specific signal that we see from this analysis is that due to the oscillatory behavior of the of this massive particle, which oscillates in the standard way is e to the IMT. And this oscillation basically in co-moving unit, because we are computing this correlation function in co-moving momentum, basically gives rise to this specific oscillatory behavior in log k, with the frequency of the oscillation exactly set by this mass of the particle. So we can go about constraining the mass of the particle by specifically constraining the shape of the particle and figuring out the frequency of this oscillation. And we can also do the same for the angular dependence, and that will tell us something very specific about the spin of the internal particle. Okay. Okay, so here's some illustration just to show you the signal. So yeah, here I'm also showing you the standard, very well-known resonance signal in usual collider physics, where if you plot the cross-section versus the central mass energy, we'll see a specific resonance. And the location of the resonance tells us about the mass of the particle that was being produced in the collisions. And similarly, if you plot this 3-point function or 4-point function as a function of this momentum ratio, we'll see a similar oscillatory feature. And the oscillatory frequency tells us something about the mass of the particle in Hubble units. So this is the way we can actually go about doing a similar collider physics in cosmology. All right, so I probably don't have time to talk about the rest of the talk. How much time do I have?
You can have like 5 to 10 minutes to end with spin.
Okay, yeah. I'll just spend a few minutes on basically briefly summarizing this part. Okay, so in the zeta space, the scalar correlators we just obtained are relatively simple, but we want to also consider more general correlators involving some extra spinning particles, which, for example, is relevant for primordial gravitational waves. So fortunately, instead of resolving the previous differential equation with all the tensor indices, it turns out that computing this diagram, actually, there's a much more efficient method. And that is basically we can construct this special differential operators called the wave shifting operators, okay, or spin raising operators. Take this simpler seed function that we have just solved for in terms of the scalar particles, and then simply acting with this differential operators, we can generate these spinning solutions. Okay, and basically we have to conserve conformal invariance throughout this process, and there's a systematic algorithm for constructing conformally invariant bases of the differential operators. So the exercise is to combine these various bases of this conformally invariant differential operators to generate the the desired spinning correlation function in the end. Okay?
And, Hayden, just a question. I suppose that this does not only apply to internal particles, right? So can you extract the graviton correlator with that technique?
That's right. Yeah, you can either spin raise the external or the internal particles. So basically, you can construct some differential operator that say takes spin j to spin j plus 1. Okay, and this will depend on some momentum, right? So by acting with this differential operator either on the external leg or the internal leg, depending on this.
Observe stuff like the square of the scalar gives you the graviton amplitude and stuff like that. I mean, structures like you have in scattering amplitudes that the square of Young-Mills gives you Einstein amplitudes and stuff like that. Is there any interesting patterns arising from that?
Yeah, so from this technique, you can compute the graviton 4-point function from the Young-Mills 4-point function. But so far we haven't been able to identify such a nice relationship between the two objects because they actually happen to be very complex expressions. So usually in the scattering amplitude context, these are very simple because they basically become like a Park-Taylor form, just a simple one-line expression, whereas we don't have such a nice formalism, like spin helical formalism. We also do have in cosmological, but they're not as powerful as in flat space. Yeah, this is actually something that we are currently working on. So hopefully we can have more idea about this in the future.
Cool.
Okay. Let me skip this. Yeah, so the idea is that you can obtain various spinning correlation function like this graviton Compton correlator using this phase shifting operators. And then check that it satisfies the word identity that this spinning correlation should satisfy. And one last thing that I want to mention is that there's also a different way of getting this spinning correlation function in DS, which is by starting from some flat space correlation function or the wave function, and then applying with some different set of differential operators, which we have called the transmutation operators that transmute this flat space object into this object. And why we are doing this, because in flat space wave functions are simple to construct because they only have this simple poles, as I mentioned previously. So it's relatively easy to construct this object in flat space, and then we can lift this flexible object to this other space by finding a certain set of differential operators. Basically, these flat space objects just have simple poles. These residues are given by this flat space amplitude. And from this, we can construct this corresponding de Sitter objects by finding some certain set of transmutation operators. All right, so let me now conclude. So far in this talk, I described the Bootstrap approach to cosmological correlation functions with the wave function, which basically can be summarized into this main point. So first, these cosmological wave functions or correlators have singularities when the sum of all the energy equals to 0. And at this singularity, the correlators are precisely reduced to the corresponding amplitudes in flat space. Okay. And a related point is that unitarity implies a certain cosmological cutting rule for the wave function, which tells us about the factorization property of this wave function. And in addition, for more generic processes, symmetries can be very useful in constraining the shape of the correlation functions and can put very strong constraints on the allowed shapes of these correlation functions. And lastly, I briefly mentioned that more complicated correlators involving spin can be either transmuted or redshifted from simpler seed functions involving some scalar particles or some flat space objects. Okay. As I try to demonstrate, I think the combination of these ideas provides a very powerful set of tools to efficiently bootstrap these correlation functions of primordial fluctuations. And I should also emphasize that this kind of no way exhaust the list of all the bootstrap constraints. And we are just starting to understand the rich connection between the structure of correlation functions and scattering amplitude in this minimal setup. But it will be very interesting to generalize these constraints to more general inflation models or even some alternative scenarios to inflation. So yeah, I'll stop here, and thanks a lot for your questions and attention.
Thank you, Hayden, for your great talk. So well, we have some time for questions. So if anyone has one, please go ahead. I see that Francisco has a question. So go ahead. Hi. So you're muted, Francisco.
Okay, thanks a lot, Gabriel. Hi, Hayden. Thank you for the talk.
Hi.
A quick question. Is there any particular limit in which the you have a three-dimensional CFT, right? Or you have approximately conformal field theory on 3 dimensions, right? So is there any particular case in which the dynamics happens in 2D, in 2 dimensions, such that, since of the infinite enhancement of conformal symmetry that happens in 2D, could that help in some way to constrain or, predict some universal feature of the correlation functions?
Yeah, so the infinite set of symmetry you're talking about is the Virasoro symmetry in 2-dimensional CFT.
Yeah, or just with symmetry, without central extension, anything like that.
Yeah, right. Yeah, good question. So right now, we are not really defining a dual CFT per se in this business. So we are not really using DS-CFT correspondence in this analysis, but we are simply using the fact that this correlation function happens to be kinematically conformally invariant. Okay. Yeah, so we haven't tried to utilize some extra symmetries that we might have in specific dual CFTs. But yeah, it will be also interesting to see whether we can actually start from some boundary theory and then use some extra symmetries to see if it can give some very specific signatures of these correlation functions. Yeah, we haven't really done that analysis yet. We're just looking at this bulk correlation functions, so to speak, and then try to use conformal symmetries just kinematically to constrain these shapes.
All right, okay, I see. Okay, thank you.
Okay, I see that Spiros have a question.
Yeah.
Go ahead.
So can you go beyond the 4-point function? Can you talk about endpoint functions?
Oh, yeah. Yeah, so endpoint function, I think if you reduce the tree-level processes, then it should be global. So it just, yeah.
So all these constraints, they also constrain the endpoint functions in general. You can write down a general formula for an endpoint function.
That's right. Yeah. So the constraints that I talked about in this talk, like all the singularity behaviors, unitarity, and the symmetry constraints, they all apply to arbitrary endpoint functions. So in principle, you can use this principle to construct this high function.
And have you talked about any arising patterns that you can use and try to resum, let's say, endpoint functions and talk about the wave function? Well, the wave function is essentially some PDF if you want to think in statistical terms. Have you ever thought about probing the whole PDF instead of endpoint functions through these resummation techniques that might appear? Or
yeah, good question. Yeah, I know that you guys have been have worked on kind of PDF and resumming the endpoint function. Yeah, so in defining this wave function, sorry, I'm hearing some echo. Sorry.
that's probably me. Sorry.
Yeah, so in defining this wave function in the beginning, yeah, I'm basically assuming that we can do this perturbative expansion around the Gaussian piece, so that there's a straightforward relationship between this correlation function and the wave function in this manner. It's not so clear when you go beyond this perturbation theory. It's not so clear what the relationship is between the wave function and the correlation functions. So for those scenarios, it might be, I think, better to just directly look at the properties of the correlation function rather than starting from the wave function.
And would you say the same about the loops? For example, if you stay at the two-point function and try to see higher loops, would again this psi would be not straightforward connected to the actual
not straightforward. Yeah, so it's not straightforward. Yeah, once you include higher loop processing and try to resum the loops. For example, you can try to compute this propagator involving infinite set of bubbles, as we usually do in flat space. It's not so clear how to do this from the wave function perspective. Actually, there are some people recently that have done this at the level of the correlation functions. So by basically computing this bubble for the correlation function, you can try to resum this bubble diagram directly for the correlation function, but it's not so clear how to do this from wave function. So yeah, there are some complementary ways of studying correlation functions. This wave function perspective is particularly useful if you restrict to the perturbative processes.
I see. Thanks.
Okay, I see that Gonzalo has a question.
Yeah, this is a related question really to what Spiros asked. Is the this Bootstrap program constrained to perturbative techniques, or it's possible to make a non-perturbative statement? For example, if I guess what Spiros had in mind is okay, you want to have the, let's say, the PDF from the wave function, and then you want to probe large amplitudes, for example, where perturbative techniques start to fail. And so will there be some sort of way of making general statements about the, let's say, the PDF for large amplitudes, for example, on the tails?
Right, yeah. So yeah, this is all very good points, and these are kind of the questions that people are starting to actively thinking about these days. Yeah, so yeah, because we now kind of think we understand like the perturbative properties of the wave function, we want to kind of go beyond the scenarios and whether we can learn anything about the non-perturbative processes. Yeah, so people try to like study this kind of bootstrap constraints directly at the level of correlation functions in a restrictive setting where you have the full set of conformal symmetries. So yeah, just like the conformal bootstrap literature. So some of the conformal bootstrappers have recently wrote a paper where they want to use the set of de Sitter isometries to fully bootstrap the correlation function, not the wave function. It seems that so basically let me see if I can summarize the so if you have some 4-point function of 4 fields or operators, the usual bootstrap constraint is that you can factorize this into 3-point structures in this way with some coefficients, right? Squared. And the usual conformal bootstrap context, this coefficient is positive, so you can utilize these positive constraints to learn something about the this structure of the 4-point function in terms of this so-called OP coefficient. And this is in the ADS-CFT context, but people have also recently looked at this 4-point function in de Sitter context. So we have very similar positivity constraints for this de Sitter object, but instead of having this finite or discrete sum, we seem to have some integral of the conformal weights of some function f which is called spectral density. And this is some conformally invariant structure, so basis functions, conformal partial waves, it's called. Yeah, and then, yeah, the constraint is that this F has to be positive for unitary theories. And so, yeah, people are now trying to use this particular positive condition to see if can learn something about the 4-point function in de Sitter. And because this is a non-perturbative relationship, you can try to learn something about the non-perturbative processes. And yeah, so in the restricted setting where we have full set of conformal invariants, we can try to play with this bootstrap constraint. In other more general scenarios where this the probability distribution completely breaks, like this is symmetries. Yeah, it's not so clear whether yeah, this bootstrap constraint can provide us, can say anything useful at this stage. But I think in any case, the partial set of constraints that I talked about, like the singularities and unitarity cuts, they should still apply to these processes. Yeah, so do you know, like, do you assume some special property of this probability distribution in this context? When you have very large tails, do you assume anything about the specific tail behavior, or?
Well, that's what I wanted to learn. No, I don't have any.
I don't know specific model, I guess.
No, I mean, well, a couple of weeks ago we had a talk by Paolo Criminelli where he discussed these, I mean, non-perturbative techniques to uncover, let's say, the shape of the tails. But he will be using some sort of toy model based on Lagrangians, for example, a certain type of Lagrangian that will give a very interesting shape for the tail. But I wouldn't be able to connect that with your approach with the bootstraps. Perhaps there is no overlap between both formalism. Perhaps there is. So yeah,
right now, yeah, there's no clear connection between, yeah, for example, the formalism of Paolo Criminelli and the formalism that we are studying.
Yeah. So I'm not sure. Well, I haven't thought enough about it, but perhaps that Lagrangian does respect many of the symmetries that you consider, or maybe not.
Right. Yeah.
I guess
so Lagrangian, yeah, he writes down like has certain symmetries. You can try to exploit those symmetries and try to see what the consequence of this, like as some form of this differential equation that this probability distribution has to satisfy, and things like that. So it's possible that there could be some bootstrap constraints for this models with large tail in the probability distribution. Given that.
So sorry. Just a last question. When you discuss symmetries here in your talk, okay, the obvious symmetries that we will all love and commit to our rotations and translations, but can you replace those other symmetries that you used by other symmetries to get similar results, but which differs from you just because of you? Has people tried to choose other symmetries that are not conformal or will that, like?
So for example, you can have like so these are space-time symmetries that we are imposing, and people have tried to generalize from this conformal symmetry. For example, if you have some very specific inflation model, like a solid inflation and things like that, more general EFT type of inflation setting, you can try to use different symmetry principles. And for example, the group in Cambridge have done something like that. So they were able to classify all the graviton 3-point function arising from this more general symmetry breaking pattern. So yeah, that's one possibility. And another interesting set of classes of theories is that theories with shift symmetries. For example, you can have some very scalar fields with some various types of Shift Symmetries. You can try to compute correlation function in those theories. So you can also try to use some different symmetry constraints. And there are some people working on this this bootstrap constraint on this shift symmetric scalar theories, also in Cambridge and in other groups.
Yeah, fair enough. Mm-hmm.
Okay. Any more questions? Well, I hopefully I have one question. Hopefully it's very short. Could you go back to the slide where you discussed symmetries? Yeah, that one. Yeah. So I have a question. Well, I think that, well, are those water identities, right?
Yeah, these are the so-called conformal
Okay.
water identities.
So my question is, if you have something, if you have like a symmetry breaking of SCTs or dilatations, do you still have those water identities, or it's they're changed in some way? Yeah,
so if you're breaking the symmetries by some strong amount, then the symmetries are no longer good symmetries of your problem. But you can also think about breaking them just mildly by giving a small inflaton. So in this case, here I've written down the formulas explicitly for these conformal scalar fields, which have this scaling dimension exactly of integer dimension of 2. And this is for conformally coupled scalars. If you have massless scalars, exactly massless, then this dimension will become 3. It will shift some of the coefficient by some integer amount. But you can consider giving some small mass to the inflaton, like a root epsilon Hubble or something like that. In which case you will also shift this to 3 minus epsilon, something like that. So you can still try to solve this conformal wide identity for this general inflaton with a small mass by expanding in terms of this slower parameter. This was what I was talking about to Spiros at the beginning.
Oh, okay. So it depends on how much do you break it, right? Yeah, exactly. Okay. Yes. Okay. Well, I see that Francisco has a question, so let's say that that's the last one. Okay.
Okay, thank you, Gabriel. Hayden, sorry for going back again to the previous question that I had, but is it true that in the 3-point case, in the 3-point function case, because momentum conservation, the triangle is in the plane, right? So would that mean that if the 3-point function is effectively, on a plane, so would you have then like the full power of a 2D CFT in that case? Or since it's the 3-point function is already fixed by the symmetries and there's nothing really new.
I think this triangle in the plane can still rotate in the 3-dimensional space, so it's not exactly the same as computing the 3-point function in 2D CFT, right? Because this triangle can rotate in 3-dimensional ambient space. So it's not so clear whether you can constrain this 3-point function. Actually, the 3-point function in 3-dimensional CFT is completely fixed by
the symmetries, yeah.
So, and yeah.
All right. Okay. Thanks.
Okay. So unfortunately, we are out of time. So let's thank again Hayden, and thank you everyone for coming today. Take care and have an excellent rest of the day. Bye, everyone.
Thanks a lot for the talk.
Bye.
Very nice.
Bye. See you around.